rush it. I had another meeting after our session, but now I have more time, so let's do this. Okay. So I don't know if you recall last time. So what we did last time is that we went into PipeSim Canvas, and then we built a well from scratch. And then we ran nodal analysis. Today, what I plan to do is actually I need to again go to, but in a quicker, go to the same steps, but in a quicker. I will not spend the same time that I took last time. So and then from there we are going to change the conditions so that we add gas lift system. Okay. So what I'm gonna do right now is that I'm going to add a casing, right? And then I will add a tubing, and then I will add. I'll make this tubing, for example. So this casing right now goes to 10,000. So I'll make this casing. I'll use the detailed pan. So I'll go make the casing go all the way up to, let's say 7,500, for example. And then the tubing goes all the way. So the tubing, so right now the inside diameter of the casing is 4.7. I will make it 6 inches. All right, and then we have one tubing. So the default tubing is 1.59. So I'll make it 3.5, for example, as the inside diameter. And then I'm going to make this tubing end up to, let's say, 7,000. So right now the casing is up to 7,500. I will make the tubing goes all the way up to 7,000, let's say 300. All right. So now this is our casing and tubing. Next, I'm going to add a packer so that I will restrict the flow to go inside the tubing. So I'm going to add a packer here. I'm just dragging and dropping, right? Now let us see how if and one of the things that we didn't add last time is the deviation survey. So deviation survey last time we said that we are going to use vertical. Now I'm going to do 2D. So the main difference between 2D and 3D is the fact that in 3D we have to also enter the azimuth, but this of course will not affect the hydraulic calculation. So most of the time we will use the 2D. So I'm going to add let's say a deviation survey, so 0 0. Then I'm going to add, let's say, maybe 7 or 8 points. So from 0 until, let's say, 4,000, it is vertical. So 4,000, 4,000. And then now I start to deviate. So you'll notice that while I'm adding these points, the curve will be updated. And usually the MD must be must be equal or more than the true vertical depth, because if we are deviating, then the length will be more than the true vertical depth. So let's say at 4,300 we have, for example, 4,280, and then at, let's say, 4,800 we are going to have, let's say, 4,700. Then at 4,000, let's say, or 5,600, we will have, let's say, 5,450, or let's say 5. Yes, that's fine. So let's say at, for example, 6,200, we are going to have, for example, 5,900. Okay, let me probably fix this one just to make it a bit shallower. So I'll make this to be 5,000, let's say 800. So let me, yeah, that's fine. I'll fix it later. And then I'll go to, let's say, 7,000. 7,000, this will be, let's say, 6,200. And now I need to add, of course, I need to cover the whole deviation survey. So the last point, I'm going to make it 7,500. And then I will make this to be, let's say, almost horizontal. So it will just increase a little bit in the TBD. So 6,250. As you can see here, this is the angle, and the angle. So for example, the angle here, I need to make sure that the angle is always increasing. So now let me make this one a little bit less. So I will make this one, for example, let's say 290. And then this one will become, let's say, okay, 750. Yeah, this looks better now. So as you can see here, this is our deviation survey. Okay, this is our deviation survey. I need to remove any validation. We have now this validation, so I'm going to delete this row. Right click and delete, and then we have now this is our deviation survey. So the deviation survey is used to calculate the angle of the flow. Like for example, we assume that this is the casing, all right? And for the pressure drop calculation, the angle matters, okay? So if you have horizontal angle, will different than the vertical angle, because then the holdup will be different, okay? So I have added now a vertical, horizontal, deviation survey. One of the good things about the canvas here is that I can go to home. I can go to format, and then I can make the format looks like, as it appears in the deviation survey. So something like this, okay? Next, so I have added now the tubular, right, casing, and I also had added the deviation survey, and then I have added also a packer. At this stage, I'm not going to add any artificial lift. I need to mention the heat transfer. So for the heat transfer right now, I'm going to make it one. Let's leave it as single point, which means that the heat transfer between the surrounding and the fluid is 2. Basically, this is the total heat transfer coefficient, BTU per each degree Fahrenheit by the foot square, because this is basically the enthalpy, and it looks into the degrees or the temperature difference between the earth and the fluid, and this is how it calculates the heat transfer between the fluid and the surrounding. And then we enter the soil and soil temperature here at the wellhead. Then in the completion, I need to add a completion now. The completion now needs to be at least or maximum at the casing depth. So if I add a completion now, so then I will make that my completion depth is at 7,500 also. All right, or I can make it a little bit higher, 7,450. So this is our completion. Okay, now last time I didn't go into all the details. So here we have the way we describe the IPR or the data needed for the IPR depends on the IPR model. Okay, as I said, we have productivity, well, PI, we enter the well productivity index. So all of them requires, reservoir temperature. Let's say I have a reservoir temperature of, let's say, 2,900 PSI, and the reservoir temperature is 200, for example, and then the IPR basis is liquid. I will enter that, then the productivity index. Let's say the productivity index is 5. Now the plot didn't generate. The IPR curve is not generated because I did not add the fluid. So I need to add a fluid now. So let me go and add, for example, at this stage, let's add heavy oil. All right. Just to, so this is currently, for example, API is 26. So let me also assume that the GOR is also low. So let me assume that the GOR, the gas oil ratio is 2,500. Okay. So that, you'll see the impact of the gas lift later on. So now we have added this fluid. I can, improve the way I describe all the options for the flow correlations. I can even add some of the measurements, some of the measured fluid values, but this is a bit advanced right now. We don't need that right now. So the most important thing is that I have added API of 26, all right, which is heavy, and then low GOR. And then also I made the water cut 0 at this stage. So with that, if you go to the reservoir, you will see that, okay, this is our IPR curve, okay. And now, so in this IPR curve, we find that, okay, this is the absolute, this is the absolute open flow. Absolute open flow is the intersection between the IPR and the zero flow bottom hole pressure. So this is the flow bottom hole pressure, and this is the flow rate. So at this stage, we're talking about probably something like maybe 11,000. So what I can do to look into the data, I can click on this small grid here where I can view the data in this curve. So if I click here, then this will be converted into the table. So now the last point here represents the flow bottom pressure, which is 10,708. Okay. Now I'll go back to the curve. Now what I want to do, I have built my model now, all right? And then I need to make a quick run in my nodal analysis, okay? So let's assume that I am running my nodal analysis, and then I need to add the bottom hole, the nodal point to be at the bottom hole. So it will put it automatically by default on the top of the first completion, or at the same depth as the completion. And now I need to run this nodal analysis against wellhead pressure of, let's say, 350 psi. Let me see if now this will flow naturally. Well, it is flowing actually. So I need to now make the situation a little bit more difficult so that I can utilize the gas lift system. So what I will do is I'm going to go back to the completion. I will click here. So it's interactive. So I can click here right away. And then I will make this reservoir pressure to be, let's say, 2,600, for example. Now I'm going to run my nodal analysis again. For the same, so I need to reset now because I have changed. You see now this is the reservoir pressure. So for the same wellhead pressure 350, let's run this now. And now the flow rate has decreased a little bit. So now what I'm going to do, I need now to add a gas lift system where I need to boost my production from, let's say, 2,400 to, let's say, 4,000. All right. So I need now to add an artificial lift system. This artificial lift system will be a gas lift system, right? And then my objective is to increase the production from 2,400 to 4,000 barrels per day. Any questions so far? If you have any questions, we can cover any questions so far. Otherwise, I can go to the gas lift system. So this is my operating envelope right now, and this is my bubble point. And as I said in the last time, the operating envelope is basically defined by, number one, the inflection of this outflow curve where it starts going up, because if the intersection happens on this section here on the left hand side, then the production will be considered unstable. All right, so this is my first limit. My second limit is the erosional velocity, and then the minimum is basically the percentage of the absolute open flow, and then the maximum will be the reservoir pressure. So this is my operating point. Okay, so no questions. Let's go now to the gas lift system. Okay, so what I'm going to do is that I'm going to let me just hide the video panel. So now I'm going to, so I have different options here. Before I go to the gas lift, let me also show you that we have also other tasks here in basically the well editor. We have what we call the PT profile. PT profile is nothing but a different way for calculating the well performance. So nodal analysis, how does nodal analysis work? So nodal analysis basically will draw the inflow curve. It will also draw the outflow curve and then find the intersection. Okay. The PT profile will basically find this operating point without inflow and outflow. So you go to the PT profile, and then PT profile will tell you, so you need to specify what are you calculating for. PT stands for pressure temperature. So what are you calculating for? I would say that I'm calculating for liquid rate. So this is my calculated variable. I need then to specify the outlet pressure. In our nodal analysis, it was 350, correct? So now I can run the nodal analysis, the PT profile now. And then of course I'm going to get the same result. And as you can see here, this is the pressure profile, and I can also show the temperature profile if I want, or I can show any other parameter if I want. But if we go now to stick to the PT to the pressure, so as you can see here, this is the reservoir pressure. So the reservoir pressure is 2,600. Then I have lost all this pressure between the reservoir until I reach to the bottom of the well, because this is the drawdown now, the pressure drop. And now from this point to this point, this is the pressure gradient along my tubing until I reach the wellhead pressure. As you can see here, this is my wellhead pressure, and it is at 350, remember? And I can do the same thing. I can here click on the grid, and I can view the numbers as well, right? So this is the elevation change, and this is the pressure. Okay. So going back now, so this is my PT profile. In PT profile, I can also run sensitivity analysis, for example, if I want. I can have, let's say, I can see the impact of wellhead pressure on PT profile. Let's say if the outlet pressure is changing from between, let's say, 300, 350, 400, and 450, then you will see that I'm going to create multiple PT profile curves associated with each of these wellhead pressures. So when I click on run, as you can see here, I'm going to have multiple outflow curves or multiple PT profile curves. Each one is associated with one flow rate. Okay, this is doing sensitivity using the PT profile task. Okay, now let's go to the gas lift. Okay, as I said, I'm going now, and the gas lift we have multiple tasks, right? What we can start up with is, let's go to let's say the first task, which is the deepest injection point. I need to define my deepest injection point. Okay, and this will help me in the gas lift design later on. So what do I do now? So I need to define my boundary conditions. So I say that, okay, I need now to produce again the same wellhead pressure, which is 350. This is the reservoir pressure. This is the reservoir temperature. This is the GOR, and this is my water cut. Now the injection parameter, I need to define my operating injection pressure. This will be taken from the field. How much pressure can you provide at the wellhead to inject the gas? Okay. So right now, operating injection pressure is, let's say, 1,500 psi. Surface injection temperature, let's say that now we have, for example, the gas injection temperature is, for example, 40 Fahrenheit. And then target injection rate, how much do you want to produce? Okay, no, sorry, target injection rate is how much can you inject in this well. All right, so let's assume that we are going to inject, let's say, 3 million standard cubic feet per day. This is the target injection rate, and then I'm going to use gas specific gravity for the injection is 0.64. Okay, now all this is to calculate how deep can I go. Okay, how deep can I go? So now I click on run. Now this is my results. Okay, so deepest injection point, I can go up to, the last point. That means I'm okay. I have no problem. So my deepest injection point is just above. So this is taken from. So we have now two. This is the pressure, okay, of the wellbore, right? And this is the casing pressure, and this is the deepest injection point. Okay, so now when I have this result, okay, I can now go to my gas lift design. So I now have my deepest injection point is 6124. Let me compare this value with the packer depth. Okay, so if I click on the packer, let me just take this. So my packer is at 6854, and this is my deepest injection point. So I need to inject somewhere here. Okay. Good. So now let's close this. Let's take this. Let's remember this value. So 6124, and now let's go to the gas lift design. Okay, to the gas lift design. So close this one, and then go to gas lift, and then gas lift design. And now I need to spend some time here a little bit, because there are a lot of basic options and some number of advanced options that I don't think there is a you at this stage you need to learn them, but let's go one by one. So number one, this is the boundary conditions. So what does this system do? So this is the, I don't know if you studied in the university, but this is the what we call the graphical gas lift design process. All that will be done automatically using the software. So now what do you want to do? So I want to put the boundary conditions. So production outlet pressure, this is the wellhead pressure. Okay, so 350. Unloading outlet pressure, this is optional, so I don't need to enter it right now. But usually the unloading outlet pressure can be little bit less than the outlet pressure, but my only care right now is the operating outlet pressure. This is the reservoir pressure, this is the reservoir temperature, and this is the GOR, all that taken from the well itself. Now I will use the same values that I use in the deepest injection point. So 1500 as my operating injection pressure. The kickoff pressure, again, this is optional. All right. So the surface injection temperature, I remember I entered 45 or 40, maybe 40. And then target injection rate. So now this is similarly 3. And now this is the gas specific gravity. So now what do you want? What is the calculation options? Okay. Now the injection gradient, do we need to include friction losses or not? Usually we do. The top valve unloading temperature will be controlled by the injection. Now the top valve and the bottom valve unloading temperature, both of them I can either so these are either controlled by the injection fluid or by the production temperature. So right now let's use the injection fluid. All right, and now these are a bit advanced, so the spacing control. So this is the maximum injection TVD. As you can see here, it was automatically taken from the deepest injection point, the one that I just ran. Okay, and then let me just skip these different options here. What matters to me is now this one here, the valve selection filter. What are the valves that I want to use? And this depends on the manufacturer. This depends on which contractor I'm dealing with. And then I can define from each manufacturer what is the valve size, and the valve Z series, and then the minimum port size. Okay. All that based on either inventory or sometimes cost. So now with these conditions, let us now run this scenario. Okay, so when I run this scenario, so I have now this wonderful curve. Let me just expand this a little bit. Okay, and now I don't know, I'm sure you know, if you studied gas lift, then you know this curve very well. All right, so let's study this curve here. So we have this blue line here. This blue line is for the casing gas pressure. This is the injection. This is the injection gas pressure. Okay. So this is the gradient, and now this is the production, you know, pressure, the flowing pressure. As you can see here, this is the reservoir pressure, and then this is the flowing bottom pressure. Now, this is the production. And as you can see here, at each of these points, we have what? We have the operating valve. So sorry, we have the unloading valves, and then the bottom one will be the operating valve. Okay. So what is, if you remember, what is this curve here? So this curve is the liquid level pressure taken from the reservoir, and then parallel to that, we put the first valve. Okay. So we put the first valve, and then this basically this is the offset, all right, between the valve open and valve closure, and this is basically taken from the valve characteristics. So now, so we will put the first valve at this depth, and then we go horizontally, and then we also take the gradient to this point, and then we go here. This is our second unloading valve. So all these are the unloading valves, and then this will be our, you know, operating valve. All right. So now I can look into the summary, output summary. Sorry, let me go to yeah, this one here, the grid. So as you can see here, I have now the depth. So this is the you know, pressure. This is the operating pressure, right? And then we have the casing gas pressure, right? Then we have, this is the so this is the valves. Okay, valve opening pressure, and these are the depths basically of the valves. So as you can see here, we have 3 unloading valves and 1 operating valve. Now if I like this design, all right, I can go now and basically say that, okay, I will install this. So I go to the design results, and now as you can see here, based on the curve, this is, you see, as you can see here, there's a button here called install design. So if now I go and install this design, and I close, I go back to my well, and I see that it has automatically installed my valves. As you can see here, each of these, you know, valves are installed based on the manufacturer that I selected. And now I can go and run my PT profile, for example. So let me just remove the sensitivities, and then I hit the run button. And now we manage actually to produce up to 5,200. So this is the impact of the gas lift. Now, how do I said I want to produce only 4,000. So now what do? I can basically now choke back the well. Okay, I can increase the back pressure by installing a choke. So let's do that. So what we can do is that we can go to the surface equipment, and now we can basically add a choke. So insert, and then I'm going to say, for example, I have, let's say, a junction here, and then I'm going to put a choke here, and then let's connect the well with a choke, and then from the choke to the junction. Now we have a choke at the wellhead, right? So now I need to enter the choke data. So I can specify, let's say, the choke beam size. Let's say the choke beam size is, for example, 3 inches. Now let us see the impact. So when I go back to my PT profile, for example, then the branch end, I need to change it now to the junction. Then if I run it, okay. So now I have now for choke diameter of 3, I have this rate. Now I can go and make some sensitivities on the choke size. So if I say, for example, the start point is, let's say, 0.25 inches until 3, and step for me every, let's say, every 0.5 inches. So these are the steps. Let me see which one is closer to our target, which is 4,000. I'm now doing a design for the choke size. Okay. So when I click on run, so as you can see here at 0.25, it says unconverged result, meaning the well cannot flow. And now I have, you see now the impact between 0.75 and 1.25 is significant. So probably we'll need to find a choke size between those two boundaries. So between 0.75 and 1.25. So I'll go back to my PT profile, and then I'm going to change my sensitivities here. So I'm going to make it between 0.75 and let's say 1.25. And now the step is maybe 0.25. Click on OK. All right, let me make the step smaller. So 0.75 and then until 1.25, and then the step is, let's say, 0.15. Okay. So now let's run this. So you know what I'm doing right now, huh? I'm trying to find a choke size that will fit my production 4,000, and I found this one here. Okay. So now this is my bean size that I need to use. There is also in the PT profile a more advanced method for finding the choke size, which is, this is the calculated variable. Okay. So now I can say that if my calculated variable is custom, then I can specify, let me just remove this guy now. Then now I can specify the target rate, which is 4,000. And now I can solve for what? I can solve for the choke size. See how fun this is? So now the minimum value is, let's say, 0.75. The maximum value is, let's say, 1.25. And then the proportionality is direct, meaning as the size increases, the flow rate it will increase. But is that true? No, it's not true, because as the size, yes, true, no, correct. As the size increase, the flow rate will increase, of course, because there will be less restriction. So it is direct. So now let's run this. And now it found exactly what is the required choke size. So 1.3, let's say 7, will give us 4,000. So now what I'm going to do now, I'm going to take this choke size and I'll put it in my choke, original choke, and then I run my system. So 1.037. This is my choke. So 1.037. And now if I run both nodal analysis, for example, or PT profile, I need to do reset, I think. No, because here it needs to go to the J. You see what was different? The difference is that this 350, it was considered at the wellhead, but now I want the 350 to be after the choke. Okay. So now click on run. And now it's 4,000. Okay. Similarly, if I go to the PT profile, I will find it also 4,000. So if I click here and I say that now I need to solve for the flow rate for the same wellhead pressure, click on run, and then I will get 4,000. Okay. What is this pressure? This pressure is across the choke. Okay. This is the required pressure drop or the required pressure control so that I can reduce the flow rate, because my target was to model, was to produce 4,000. Okay. So with that, there is also one last task that I can do for the gas lift, which is what we call the gas lift response. So gas lift response is another task that is very useful. So it will tell me, okay, how much can I gain by increasing the gas lift rate? Okay. So if I, for the same wellhead pressure, 350, what will happen if the gas injection rate, let's put a range here, between, for example, zero point 0.1 and 6, let's say, million, step, let's say, 0.3. Step is 0.4. It needs also, you see if this is enough. No, 0.5 maybe. Needs, I think, maximum of 10 points, I think. So let's make this up to 5, up to 4.5. Oh, yes, now it's okay. What about up to 5? Can it accept it? No. So up to 4.5, sorry, up to 4.5. Now if I click on OK, I have now these steps. Now I need to define the gas lift surface ejection pressure, which is the same, which is 1,500. Now I can run my gas lift response. So here is my gas lift response. As you can see here, 3 is actually a really good number. And economically, I can even go to less than that. So whenever the slope becomes really small, then the economics will play a role here. So I think the best is maybe to inject somewhere here, because with this we can get 5,000. But let me just make sure that the, yeah, you see the branch end, you see I made the same mistakes. The branch end so should be after the choke. Let me run this again then. Now I'm including the choke with the 1.01 something inches. So I have the restriction. Now, as you can see here, this will make things clearer now. As you can see here, so if I think it's not really economical that I inject 3. 3 is too much actually. So that's why I need probably to inject maybe something like maybe 1.5 or even less than that, because this is more economical. So I can do this by say 1.5. Now I'm doing optimization now, as you can see here. So let's go to the gas lift system, and then I can say now that the target injection rate is 1.5. And now I can even, if I run this, I can now relax the choke a little bit. So that's producing 3,600, as you can see here. Now I can go to my choke and then relax it. Or I can even run the PT profile, okay, right away. So let's go to the choke. I can go to the surface equipment here, and then I can relax the choke. So let's make the choke, for example, 1.5, and then go to the PT profile. Now if I run it, you see now I am with lower gas lift rate, I am able to actually go to 4,500. I can do exactly the same thing. So I can say that now for me, solve for 4,000, solve for solve for the choke size, and then between again 0.5 and 1.25, and then run for me. Then now it will find for me the required choke size, 1.07. So 1.07 will actually give me the 4,000. Okay. So yes, that's it from my side. What are your questions, guys? Let's go through the questions.
Yeah. So thank you, Ahmed, for your presentation. It was really fruitful. So if anyone have any questions, he can write them on the chat, or he can raise his hand, and I will unmute him, or he can unmute himself. So first of all, I have a question, Ahmed.
Yeah, go ahead.
So what is the correlation that models the injection of of gas lift. For instance,
Okay.
when we
Okay. Got it.
when we model the flow inside the wellbore, we use a correlation based on the PVT model. So how the gas injection enter in the PVT model and can be simulated since it influences the total composition of our effluent. So the calculation is going to be changed, and how is that going to be done?
So for the gas lift, for okay, we have the multi-phase flow inside the wellbore, inside the tubing, all right?
Yes.
And this is mainly governed by the correlation. So I can select whatever correlation here for the vertical flow. So I can select, for example, any of the famous correlations here: Biggs and Brill, Hagdon Brown, Mukherjee Brill, or Kizevsky, or I can select, let's say, a mechanistic model from Olga. Okay,
Yeah.
so I can use, for example, the three phase without HD. HD is a bit small, right? So this is for the production. Okay,
Yeah.
for the gas lift itself inside the annulus, it is single phase, so it's just using a pressure drop. And that's why when we say, for example, in the if I go to the gas lift here, there is an option here that, okay, do you want to include friction or not? Okay,
Yeah.
I think this is where is it, if I say enable multi, so multi-point is a bit an advanced one. As you can see here, include friction
Yeah.
losses.
If you
Okay,
have time, like
so for that, it's just a pressure drop equation. There is no need for a correlation because it's single phase, right?
basically these are what we have for this week.
Can I go next?
Thank you so
Well,
much.
I still need like another point to talk about, and you
Yeah,
can.
go ahead. Yes.
So the thing is, uh, so when we model the multi-phase flow, if you can see the screen, when we inject gas lift here, so the
Yes.
composition in this part of the
Yes.
fluid and in this part is not the same, because here we injected the gas lift from this side and from this side. We changes the This will change the PVT properties of our fluid. So the question was that how can we model this change in PVT parameters due to the change of fluid composition?
So let me, okay, let me show you. If I say, for example, PT profile, if I run PT profile, okay.
Yeah,
Now in the PT profile, let's say, for example, we're solving for the flow rate, okay. Now I can go to the output details. If we go to output details, for example, you will see now that, for example, here, let's say we have, so this is the distance, right? This is the elevation, okay. And now we have, so this is the free gas. So this is the injection gas. So this profile actually is for the gas lift injection, right? So this is the gas lift injection. Now, if I go to the production, okay, you see here. So this is the distance. Okay, so now my so this is the hold on. Where is the one that shows the, yeah, as you can see, yeah, here it is. So now, as you can see here, we have at this depth, okay, we
yeah,
have the injection gas, right?
yeah,
And we have this gas being injected to the wellbore, okay. Now, as you can see here, the flow correlation took into consideration the additional gas flow rate here,
yes,
okay. And then it took that into the calculation. So if I have, for example, what we call multi-pointing, all that will be taken into consideration, okay. Like, for example, it will know that, okay, from the completion until the first injection valve, it's the GOR coming from the completion, which is in this case 250,
yeah,
okay. And then as the gas lift being injected, the GOR will be different, and then the hold up will be different, and then all the calculations. All that is taken care of with the flow correlation here.
I see. So the implementation of this simulation is done through the GOR.
It is both. It is actually adding, so it will calculate how much is the free gas. Like for example, if the GOR is 250, maybe it is still below above the bubble point, so all that will be liquid. Okay.
Yeah.
Now once we inject, all right, we are injecting here 1.5 million, then it will take the gas flow and it will mix it with the oil, and then it will find how much will be as free gas and how much will be dissolved. All that will be taken into consideration while it calculates the pressure drop along the wellbore.
Okay. Not
Yeah.
me. Thank you, Ahmed.
Okay.
Can I go next?
Yes, you can.
Oh, thank you, Mr. Ahmed. This was really fun, as you said. This is Abdurrauf asking. Well, I had three questions. One of them already asked by Ahmed, and you had the answer. The second one is the difference between the P&T model and the nodal analysis model. Well, I understand that in the nodal analysis model is a numerical solution, but in the PT model, is it an explicit formula or an explicit equation to calculate the pressure drop and the temperature drop?
No, it's the two methods when it comes to the flow correlations, the PVT, the frictional factors, all these calculations. It's exactly using the same engine. The main difference is that in nodal analysis, okay, nodal analysis is what is a group of inflow and outflow. So this is the inflow, all right. The outflow is nothing but a combination of a number of PT profiles. Let me just show you the points here. So if I go to edit and then I go to, where is it? Series, outflow. Okay, show the marks. Okay, now each of these points, all right, is a PT profile, meaning it is calculating the flowing bottom wall pressure starting from the surface. Okay, where and by the way, the operating point has a PT profile already. So if I click on PT, so this is the PT profile for the operating point, which is 4135. Okay, so this blue point here, okay, is the operating point. And as I mentioned, each of these nodes here, each of these points is the flowing bottom pressure considering this flow rate. Like for example, it will assume, okay, what will be the flow rate for, what will be the flowing bottom pressure? Because on the y-axis is the flowing bottom pressure, x-axis is the flow rate. So that it will assume multiple flow rates and calculate the flowing bottom pressure at each of these points. This is how it constructs the outflow. The inflow is assuming the flow rate and then calculate the drawdown. The flowing bottom pressure considering the flow coming from the reservoir to the wellbore.
I see. Thank you. Another point is that you defined the heat transfer coefficient as a constant.
Yes.
And does the Olga S model count it as well as constant coefficient, since the Olga S is a mechanistic model which solves basically the energy and mass and momentum equations?
Yes. So it will consider this value as a constant value, but remember, the heat transfer value, okay, it will calculate, it will say that how much BTU, okay, is transferred based on the temperature difference between and the area. Okay, so it will look, because we have, for example, if I have this, let's say I put multiple, let me just show you here. If I say that, for example, the temperature profile, so at 0 it is 60, all right, and then it is at 7,500, sorry, 7,500, it is, let's say, 190. So now this is what? This is our formation temperature gradient. It is changing from 190 until 60, all right, which is at the surface. Now this U value, when the system tries to solve, let me just delete this guy. when the system tries to solve for the fluid temperature, it will take this heat transfer value, and then it will compare. It will, compare the surrounding temperature with the fluid temperature, and then it will calculate the fluid temperature basically.
Yeah. So this would be a linear interpolation of
It is,
the
yes.
yeah. So it's not basically solving the heat
It
the
is.
energy equation.
It is not. It is just using this heat transfer value right
Yes.
away.
Okay.
Yeah.
Okay. I see.
Yeah.
I think. Thank you so much.
Okay. Questions?
We have a question. Someone is asking, what is the purpose of T curve? It is it just used to set the right choke valve size? I think you answered that for Abdurrauf.
As I said, I mean, the PT profile is just different representation of, and it has different capabilities. Like for example, I can set, I can ask for example, I can solve for the inlet pressure, meaning I can solve for the reservoir pressure. What will be the reservoir pressure for this rate? Or I can solve for the outlet pressure. I can say, okay, if I want to produce, let's say 3000, what is the required outlet pressure? So this is a direct calculation. Unlike nodal analysis, you need to do sensitivities to find the intersections.
Uh-huh.
Yeah.
Thank you, Ahmed. There is another question from Ayman. He says, is it possible to display the flow regimes in tubing when using the
So
gas
not
lift?
displayed, but you can actually look into the results. So you can, for example, go to output. There's a profile results, okay, and then under profile results, you can see, you can go to grid, all right, and then my machine hacked. What's happening? Yes. So you can, so as you can see here, this is the pattern here. Okay. So gas lift pattern and oil water pattern. Okay. So now as you can see here, we have liquid. So this is starting from the reservoir. This is liquid and then distributed and then bubble flow. Okay. Now if I add water, let me just show if I add water. Let's say I go to the fluid and then I say that, okay, I have water cut off 25%. Now when I run my PT profile again, solve for flow rate. Okay. Now I go to show grid. As you can see here, since it is liquid, it couldn't find the oil water pattern. But now once we have bubble flow, then we have, dispersed oil water or bubble. Okay. And this is the different valve systems. One of the options that we can see is that, for example, right now, if I did not enable what I call the multi-pointing. For example, when I do not enable multi-pointing, then all the gas will be injected into the lowest possible valve. But if I say, for example, enable multi-pointing, then the calculation will be a bit different. And then I'm solving for, I am fixing the injection pressure. All right. So now let me solve now. So I will assume that the value will be a bit different. So it's 4,500. And now if I go to the grid, now if I click on, so as you can see here, this one, it says open. So this is the lowest valve. It's open. Okay. This is the nasal, which is also open. And then you see it is throttling. So I have now 3 valves that are open. And as you can see here, if I go to the, I can go to the, let me go to the grid again. So as you can see here, the flow regimes now are changed. So it was distributed in the beginning, intermittent, and then distributed. And now I have, this is my first valve. You see, the flow regime has changed. All right. And then I have another valve. All right. It's still bubble. So I don't have a visual representation, but I have the results here. Yeah, more questions? So let me see. Yeah. We have more questions, ladies and gentlemen? Okay, I guess that's it for today, Ahmed.
Yeah, I think. Let me see. We have a question.
Yeah.
In the gas lift injection part, does PipeSim give us the hand to make change in the valve diameter to see how it affects the injection rate?
So there are two modes of operation. Okay, right now, if I use, for example, the gas lift injection valve system, I am using a manufacturer valve with a specific parameters. Okay, I can use, for example, injection valve ports, right? And then for that, I can define directly the quantity. Okay, and for that, I can even make some of them is not even active. Okay, here I do not even have to enter the because it's a port, it will just basically inject whatever gas. So this is a good I would say way for screening your gas lift system. But if you use, for example, if you use the what we call al-Hanati stability check, then you can enter the port size. Okay, let's say for example 0.2, and then injection rate, let's say 1.5. So now with this, I can now do the calculation, and then I can run PT profile. Now this is a way to look into the stability. Okay, without using the actual valve, the actual manufacturer valve. So we have, as I said, we have two modes: fixed injection ports or injection valve system. For injection valve system, you cannot change the port size because you are actually using. Otherwise, you can go and select a different valve where you can actually select different port size, etc. Okay, but you cannot change it right away here. Yeah. All right.
Well, that sounds good for today. Thank you so much, Ahmed, for your time.
Thank you. So next time we will have the ESP design. Basically, we are going to install an ESP and see how we can select a pump, etc.
Hopefully, yeah.
All right. Thank you, guys.
Thank you so much. Thank
Have a
you
good
all
day.
for attending this session, and have a good day. Thank you.
Okay. Bye.
Goodbye.